Alright, let's continue doing some examples. So here we're looking for the volume of a solid that they've described for us. They tell us that we're dealing with what we call a tetrahedron. A tetrahedron is kind of it's a triangular pyramid if you want to put it that way. Though we don't really necessarily specify that we have a equilateral triangle as the base, or that the height of that pyramid is related to whatever the triangle of the base is. But what they're defining for us is a tetrahedron enclosed by coordinate planes, so that's the xy plane, the xz plane, and the yz plane. And then this plane, 2x plus y plus z equals 4. So if we go ahead and put those in there, I'm first going to go ahead and put in the coordinate planes. And the coordinate planes are just given by setting our coordinates equal to 0. So x equals 0 is the yz plane, y equals 0 is the xz plane, and z equals 0 is the xy plane. Then we also want the plane that they gave us, which was 2x plus y plus z equals 4. And maybe I'll make that a slightly different color. And make that more green, so it stands out a little bit better. So we've got our coordinate planes, and this one just kind of comes through and cuts through them. And there's one corner that actually has a place that's actually between all four of them all at once. That's this corner over here. We basically have a corner in at our origin point, and then yeah, just kind of cut off at the corner. We want to find what is the volume that is inside of that corner. We can actually even go ahead and use our intersection tool to kind of get an idea of what these I didn't want to put all those in there. Oh, well, no, it gave me one of them. Oh, I see what happened. There we go. Or was that? Did that give me all of them? There we go. We got the three intersections of our plane that they gave us with the coordinate planes. And one of them is actually down here in our xy plane. So our xy plane, we end up at the line that hits here, hits the x-axis at 2 and the y-axis at 4. And you can kind of see here that's hitting at 2, that's hitting at 4. That's exactly what's right underneath that plane. So in fact, this is just going to be the double integral where our integrand is this plane, because we were looking at everything that's below that plane, but still we'll only concern with the part that's inside the triangle. So really we're integrating over this region here. Maybe we'll even zoom in a little bit. This is our domain of integration that we're going to be using. And we're just going to be integrating the particular plane here. We'd have to solve it for z first, but that's what we can do. So we're going to be looking at the double integral of, now when we solve for z, this becomes 4 minus 2x minus y. We're going to be going over that region D. But we need to figure out how we're going to set that up as a double integral. Now again, this could be either type 1 or type 2. And really doesn't matter which direction we would go with it. So I'm going to go ahead and use it as a type 1. My bottom function down here is just y equals 0. That's not too hard to see. The top function here, we need to find out what this particular line is. And in fact, that's not as hard as you might think it is. Remember, this line is the intersection of the xy plane, which is given by z equals 0, with the plane that we're dealing with. So we're just going to take the formula 2x plus y plus z equals 4 and plug in 0. We get 2x plus y equals 4. Or in other words, y equals 4 minus 2x. So if we really want to write it out, we can say D is all the points x, y, where we'll come back to the limits on x in a second, but y is going to be between 0 and 4 minus 2x. Now what are the limits on x? Go back to our picture. Well, obviously we're going from 0 over here, and then the furthest we get with x is 2. That's not too hard to find. X is going from 0 to 2. So our integral, our double integral, is from 0 to 2, 0 to 4 minus 2x of our function, 4 minus 2x minus y. First we're doing with respect to y, and then x, and that's supposed to be our volume of that tetrahedron. And there's not too much to this. We just go through the motions of integration. Integral of 4 minus 2x minus y with respect to y is going to be 4y minus 2xy minus 1/2 y squared. We go ahead and plug in 4 minus 2x. Plug in the 0 actually gives us 0, so we don't have to really worry about that too much. So we end up with a 4 times 4 minus 2x minus 2x times 4 minus 2x minus half of 4 minus 2x squared. Now, of course, there's quite a bit of work to kind of simplify this. This is just a quadratic, but we end up with what we have right here is actually, 7 different terms that we need to condense down to 3 of them. I'll leave that to you, but it turns out it's 8 minus 8x plus 2x squared. Go ahead and do the integration again. Integral of 8 is 8x. This time we're integrating with respect to x, remember. Negative 8x becomes a negative 8x squared. And then we have a 2/3 x cubed from 0 to 2. That means we have a 16 minus another 16. And then this one becomes a 16/3. Or in other words, those 16s cancel each other out. You get 16/3. Now, this is actually one that we could check without integrals if you remember the formula for the volume of a pyramid. So any sort of cone or pyramid where you have some base. In fact, we don't even have to draw it as a triangle. If it's a triangle or a square or anything that you have down here, and as part of a plane, and you have a point up here, and you connect that point to every point in that base, we get what we call a cone or a pyramid. Just depending on whether or not we're dealing with an actual polygon down here or not, is when we call it pyramid. But the volume of such a thing is always given as 1/3 times the base times the height, where the base is the area of the base, whatever area of the thing that we have down there, and the height is we drop a perpendicular from that top point up there down to the plane that our base is in. In this particular case, if you remember what our picture looked like, obviously our height here is 4. We go up to the top of 4. Our base is this triangle. So in the triangle, it's a nice right triangle with you could say length of 2 and width of 4. I don't know. I just want to use base again. So our base is going to be half of 2 times 4. The area of that triangle is just 4. And so the volume that we expect is 1/3 of our base of 4, and we said our height was 4. Well, 4 times 4 is 16. So 16/3, which is exactly what we got from integration. So it's a nice check that everything we're doing with integration is not coming up with completely different answers than what we would expect. And that's always a good thing to see. Our next example is kind of an interesting one. We're going to be working with two different cylinders. We have x squared plus y squared equals r squared, and we have y squared plus z squared equals r squared. To actually draw these in GeoGebra, I'm going to go ahead and pick r equals 1, but we'll solve the problem for general r. So let's actually see what we're really talking about here. So we have x squared plus y squared equals 1, this cylinder here. Y squared plus z squared equals 1 is another cylinder here, and they intersect. And they contain a region inside both of them, and we want to find out what is the volume inside there. That's going to be a little hard for me to actually give you a good picture of that. I could go ahead and maybe draw the intersection curves. So these intersection curves might give you a little bit easier idea of what's going on there. Or we could even go ahead and maybe plot some of the surfaces. So unfortunately, I don't really know a nice way of getting all the surfaces, but I can get the top and bottom ones. If I take out the cylinders, you can kind of see those a little bit better. So we have this top part and this bottom part. They come from our horizontal cylinder. That was this one. So those are actually part of that cylinder, but they're contained inside the other cylinder. Then technically we have two other pieces going around the other way that come from the vertical cylinder but are contained in the horizontal cylinder. But you can kind of get an idea maybe of what that's actually supposed to be looking like. Maybe if I even put that in there. So it's the part of this cylinder that's contained between those two top and bottom pieces. But the point here is that we are dealing with, well, we're dealing with a circle. That's what we're working with. So that's what we're going to have to use in order to actually find out what this volume is. Now we did actually work with a circle before. We dealt with the circle with the x squared plus y squared equals 4. And then we noticed that was both a type 1 and a type 2. And so we can actually set it up either way. So I'm going to go ahead and set this up as a type 1. Keep in mind what we're doing there is using x squared plus y squared equals r squared and solving that for y. So that means that y equals plus or minus the square root of r squared minus x squared. This is two different curves. The top semicircle has the plus sign, the bottom semicircle has the minus sign, and those are going to be our limits for y. Of course, our x values are going between negative r and r. And so that's the information that we're going to use to set up our limits. To find out what goes inside, we have to deal with what are the top and bottom surfaces. So here, this is something that we haven't done yet. You can find the area between two curves back in Calc 1 by subtracting the two functions that you're dealing with. Well, here, to find the volume between two surfaces, we do exactly the same thing. We are going to solve this thing to find out what z is in terms of x and y. In this case, it won't depend on x, it'll just depend on y. We get z equals plus or minus square root of r squared minus y squared. And then this is two different surfaces that we're going to subtract. We can say that our volume here is the double integral negative r to r, then negative square root of r squared minus x squared. We have r squared minus x squared. We subtract those, so we have square root of r squared minus y squared minus a negative version of itself. So in fact, we end up going plus this same thing. So we'll just go ahead and put a 2 there. we do dy dx. Okay, so what do we do with that? Well, unfortunately, you can kind of see that it's not going to be an easy thing to work with. This integrand is actually not easy to integrate with respect to y. Maybe this is not the way we want to set it up. Maybe it would be easier if we do this as a type 2 instead. It's not impossible to do it, but you might have to do some sort of trig substitution. Let's see if we can get away with not doing that. So this would be as a type 1. What would it be as a type 2? In that case, we'd solve x squared plus y squared equals r squared for x instead of y. So we'd have x equals plus or minus the square root of r squared minus y squared. In fact, this form is exactly what we have here. That might be a good sign. Y is still going to be between negative r and r, just like we had for x before. In fact, a lot of this is going to look very similar. Instead of having x's, we have y's, so we have essentially the same kind of thing here. The integrand doesn't change because that doesn't depend on how we set it up. And then we do dx before we do dy. So it looks very similar, but the second one will actually be a lot easier to do than the first one. Okay, so we don't have any x's in here. So when we integrate with respect to x, this constant value just gets multiplied by x. So you have 2x square root of r squared minus y squared from negative square root of r squared minus y squared to square root of r squared minus y squared. We go ahead and put those in. Remember, we're putting them in for x, not y. So this is going to be in for x. We have 2 times the square root. Let's just actually write it out. So that's put in there first. We have r squared minus y squared again from this one. We subtract 2 times a negative, so actually we add 2 times square root of r squared minus y squared times square root of r squared minus y squared. And here comes the beauty part of this. We basically, we're multiplying it by itself, so we just get r squared minus y squared instead of any square roots. We actually get that for both places. And so, since we have the same thing, we end up adding them together. This whole thing just turns into the integral of 4 times r squared minus y squared. No square roots in sight anymore, which is kind of nice. Very, very, very nice. We go ahead and integrate that. Remember, we're doing with respect to y now, so we end up with a 4r squared y. We end up with a minus 4/3 y cubed, going from minus r to r. We go ahead and plug those in. We end up with a 4r cubed minus 4/3 r cubed. But then we're subtracting. When we plug in negative r, we can have a negative 4r cubed plus 4/3 r cubed. So everything has an r cubed in it. 4 minus 4/3 plus 4 minus 4/3. All that combines to be a 16/3 times that r cubed. So actually, if I go back to our picture here, because I use r equals 1, the volume that's actually going to be inside there, inside the solid that's a little hard to picture, that volume is going to be 16/3. Which is kind of interesting that it doesn't involve pi. Probably expected it to involve pi. But it just doesn't. But as we saw from that example, picking one approach, picking the type 2 in that particular case, instead of a type 1, made the integral a lot easier. In fact, there are examples where doing in one direction can be impossible to do the integral directly. It wasn't the case in the last one. We definitely could have integrated square root of r squared minus y squared with respect to y. It just involves some trig. But if we look at 53, what we have here is we're trying to integrate the square root of y cubed plus 1. Integrating that is actually impossible to do in what we call elementary functions. There's no nice form for that integral in terms of like exponentials, logarithms, square roots, any of that kind of stuff. So this would be an absolute pain to try to do directly. In fact, I would say it's pretty much flat out impossible to just do this directly as it is written. But as what they're asking for is that if we change the order of integration, if we figure out a way that we can do dx dy instead of dy dx, then this will be a lot easier. And it'll actually be possible to do. But the issue here is that we don't know exactly what the region is that we're integrating over. We're going to have to figure out what that is from our limits. So let's think about what we have here. Maybe we'll write them out. So the x's are going from 0 to 1. So we could say x equals 0 and x equals 1 are limits that we might draw. Our y values are going between square root of x and 1. And let's go ahead and plot all of that. So our x values are going to go from 0 to 1. So we're going to be between these two lines. So maybe we'll zoom in a little bit. Our y values, our bottom y value was y equals square root of x. So we get this curve. I'll turn it black. And then, what was the other one? I think is y equals 1. Let us make these a little bit more visible. There we go. Alright, so what is the region that we're actually working with? Well, keep in mind, we're not dealing with this one over here. We're going from y equals square root of x to y equals 1. That's what we're doing. This is our bottom curve, and this is our top curve. We're dealing with this section up here. This is it can be either a type 1 or type 2. What they did was a type 1. If we change it to a type 2, maybe things would work out a little bit nicer. If we work as a type 2, now instead of looking at top and bottom, now we're going to be looking at left and right. Our leftmost curve is just x equals 0. Our rightmost curve, which they've written as y equals square root of x, we need to change that to be x is y squared. So we'd be going from 0 to y squared. Our y values are going to go from 0 to 1. So we're changing this way of writing it and making it so that y is going from 0 to 1, and then x is going from 0 to y squared. And so when we change that order, the integral that we started with should be a y cubed. I'm so used to writing square roots with squares inside of them. We generally try to avoid putting cubes inside square roots because they don't really work very nicely with things like this. But our limits become now 0 to 1, 0 to y squared. That doesn't change our integrand. We still have the square root of y cubed plus 1. But now we're integrating with respect to x first, and that might make all the difference. Or at least we're hoping it will make all the difference. And so these two things should have the same value. Especially since we have this is a nice continuous function. And as long as y doesn't get as low as -1. Once we get down to y equals -1, things can be an issue because then we put in more negative values. We get negative values into the square root. But y is between 0 and 1. So nice continuous stuff. Alright, so there's no x's in here. So when we integrate it, the integral of that is just x times whatever that is. And then when we go ahead and plug in our limits, of course putting 0 just ends up with 0, so that we kind of ignore that one. But putting in the y squared, we end up with a y squared times y cubed plus 1. And so what do we have? Well, we have something that we can do a substitution on. This is no longer an impossible integral to do. We can make the substitution u equals the inside of the square root, so the y cubed plus 1. That means that du is 3y squared dy. Of course, we don't have a 3 in here, but we do have the y squared dy that we wanted. We end up needing a 1/3 to make up for that 3. This inside becomes a square root of u, du. The limits, we go ahead and plug in the 0 and 1 that we have from here into our y cubed plus 1. That'll leave us with 1 to 2. And it shouldn't be too hard to see how to proceed here. This is u to the 1/2. When we integrate it, we have u to the 1 more is 3/2. We need to end up dividing by that 3/2, so we have a 2/3, which we'll go ahead and combine with that 1/3 in a moment. And we're going from 1 to 2. So we end up with a 2/9 times. When we plug in 2 to the 3/2, I'm going to go ahead and write that as 2 square root 2. I mean, you could write it as 2 to the 3/2 if you like, but 2 square root 2 is a little bit nicer for me. Then we plug in 1. Well, 1 to the 3/2 is still just 1. And that is our answer. So we took something that looked almost flat out impossible to do initially, but by changing that order of integration, we were able to go ahead and solve it. Now, one thing that made that work is that they did give us a region that we were working with. If we had a different region, this may not have worked. The fact that we ended up with a y squared in front that came from our limits was actually the key that makes this work. So when we're doing double integrals over regions in the plane, the shape of the region can actually make things a little bit, make them easier or harder, just because what we end up getting plugged in from our limits actually play a role when we do the second integration. So kind of a lot of stuff going on here, a lot of possible situations, but hopefully these 7 examples that I've given you here have given you a good idea of how to approach these kind of problems. And then the book also has some various examples that they go through. I left all those for you to read through to see how they approach these kind of problems. As we go forward, we're going to actually look at some other ways of tackling these. So actually, a couple of the problems we already went through dealt with finding integrals over disks. Situations where things are rotationally symmetric like that, where it does feel like we're dealing with stuff going around the origin, those come up fairly often, and so we're actually going to look at working with polar coordinates when it comes to that kind of stuff. So there's definitely more situations that we'll be looking at in the coming sections. This is it's a fairly lengthy chapter that we're going to be going through here. But this is kind of the core feature, how we do double integrals using these limits that may not be just numbers. So I'm going to leave that here. We'll get into 15.3 in the next set of videos. So I'll see you then.